Hello. So, we will continue our discussion of computing a maximum matching in a graph. In the previous lecture, we had a few results. The first one that we described was a characterization of maximum matching. It says that in a graph G VE, a matching M is maximum if and only if G has no augmenting path. With respect to M. So, this allows you to know whether a matching M is a maximum or not, provided you can compute an augmenting path or decide that there is no augmenting path in the graph. So, the problem reduces to compute an augmenting path, but the question is, how does that help you compute a maximum matching? So, for the computation, if you have an augmenting path, let us say in the graph, where V1, V2 and V3, V4 are the matching edges in M. So, this is inside the graph G. Then we can modify this into another matching. With U1 V1, V2 V3 and V4 V2 as the matching edges, and those original matching edges have been rendered non-matching edges. One can verify that this set of matching edges along with the other matching edges in the graph still constitutes a valid matching. But the advantage is that we have augmented that matching. The new matching has one more edge. This way, we can improve the size of the matching every time we can compute an augmenting path. So, this is not only a characterization, but also a way to compute a maximum matching. Now, so the problem now reduces to compute an augmenting path. Now, in each step, when we compute an augmenting path, we can improve the matching size by 1, and a matching cannot have more than n by 2 edges, n being the number of vertices. So, one may have to compute this n by 2 times. So, the cost of computing a maximum matching will be order n times f, where f is the cost of computing an augmenting path. The second thing we did, we described a graph based on the original graph and the given matching M. So, suppose we have graph G, and these symbolically denote the set of unmatched vertices. The U is the set of unmatched vertices, and this is graph G. Then we defined a graph H, which we denoted by G modulo u as this, where we contract all the vertices of u into a single vertex S and do not modify these vertices and the edges. So, for symbolic simplicity, let me just denote that this is a map. How does that map the vertices? So, any u in capital U maps to S, any V maps to V for all V in V minus U. Okay, I made a mistake. This is capital U. Any unmatched vertex goes to S, any matched vertex goes to itself. In addition, phi of UV is SV for all U in U and V in V minus U. Further, phi of V1, V2 goes to V1, V2 for all V1 and V2 in V minus U, and finally phi of U1, U2 is undefined for all U1, U2 in U. This is effectively what we achieve here. So, note that as far as the edges of this graph are concerned, which are not contained in the set. So, the edges of these two types, the UV type and V1, V2 type, they have a unique image here, and therefore, we can map backwards. So, for every edge in H, there is a inverse image in G. Okay. So, this is something that we will need to use later on, that defines our new graph, which is sort of reduced, which has got fewer vertices in general. Of course, if there is only one vertex here, then that graph will be same as H. Well, then taking this graph H, we defined a alternating path tree on it. So, let us just take a look at that, which we had described earlier. The set U0 contains a single vertex S. All its neighbors are in U1. Their matching vertices are in set U2. All the new neighbors are in U3 and so on. So, this has got non-matching, matching, non-matching, matching and so on edges. As these are the tree edges. In addition to that, whatever the edges in H we have, we partition them as follows. Those edges which are between two vertices of set U infinity, they are labeled as E infinity here. Those edges which run from an odd level either into u infinity or any level below this u1. So, it could go to u2 or u3, u4, anything down. They are all labeled A, and any edge, non-tree edge, which runs from an even level to an odd level, are labeled C. In addition to that, any edge which runs within the vertices of a given level, let us say in case of odd levels it will be a matching edge, in case of an even level this will be a non-matching edge. These are all labeled B. So, the non-tree edges are partitioned into these 4 classes. We also showed that this tree can be computed using breadth first search, and we can also identify all the B edges during this computation. So, this entire computation of computing this tree as well as the B edges takes order n plus m time, where n is the number of vertices, m is the number of edges in H. So, maybe I will use prime to differentiate between those numbers for G. So, this much we had done, and now we are prepared to proceed with the actual computation of an augmenting path. We had defined something called odd alternating cycle, which meant an odd cycle where there is a vertex u which belongs to the set u which is unmatched, following which we have alternately matching and non-matching edges in it. So, these 2 edges are obviously non-matching edges, and then we have the alternating path from this vertex to this vertex. And we had shown here that every odd alternating cycle in H must pass through at least one B edge. Now, please note that every odd alternating cycle in H must pass through S, because this is the only unmatched vertex in this graph. All the matching edges of G are the matching edges of H. So, we have really a graph H m with an abuse of symbol same m that we have used in G. So, an alternating odd cycle will pass through S, and the claim says that it must pass through at least one B edge. So, we are armed with this information, and now we will begin the discussion for the computation of an augmenting path. So, let us first observe that an augmenting path in G, an augmenting path call it P, 'becomes' 'P' 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 'becomes' alternating odd cycle in H. So, you take an augmenting path in P in G. What you notice is that its image, for example, if this was the path, this is U1 and U2, these are the unmatched vertices, then this will transform into an alternating odd cycle in H. This is in G. But what happens if we have an alternating odd cycle in H? Can we recover a augmenting path in G from that? Well, we have something along those lines which we will use in order to compute an augmenting path in G. So, let us suppose C1 is an alternating odd cycle in H. Then what is its image in G? Remember that a cycle is a set of edges. So, and edges in H have a phi inverse image in G. So, this is a well defined entity. This passes through S. So, there are two possibilities clearly, that this is obviously in G. So, if I do the inverse image of this, it is possible that when we do phi inverse on this, these two images may end up into different unmatched vertices. So, that would turn into this path, and this is an augmenting path. In other situation, this is not the case, and this is still an alternating odd cycle. In case both of these edges were incident on the same vertex in G, then this remains as it is. Of course, they go to that corresponding vertex. So, in that case, we have still this situation in G. This is in H and this is in G, and you have this picture. So, what do we do in case we discover such a cycle? How does that help us figure out an augmenting path in the graph G? Okay. So, then there is a result that we will now show. That if C is an alternating odd cycle in G, then G has an augmenting path if and only if G mod C has an augmenting path. So what we notice is that either suppose we compute a augmenting odd cycle in H, then when we do phi inverse, either we directly get an augmenting path, and if we don't and we end up getting an augmenting alternating odd cycle in G, then we will exploit this result. What it says is that there is an augmenting path in G if and only if there is an augmenting path in G mod C, which means vertices of C have been shrunk into a single vertex. So this is a smaller graph. We will recursively call the algorithm for computing an augmenting path in this graph, and then we will show that not only that this gives you an augmenting path, but you can actually build an augmenting path for G using this path. So we will actually recover such an augmenting path in G. So let's try and prove this claim. All right, so let's suppose we have a graph G there is a path cycle C which is odd and it is an augmenting alternating cycle. This is the story in G. So G mod C, this is this cycle I will call C. So mod C is some vertex x. This is the vertex that results from shrinking these vertices of the cycle into a single vertex. We do not touch anything else, so that stays as it is. Now first let us see if there is an augmenting path here. So let us suppose there is an augmenting path which in this graph which does not touch x. It does not touch x. So this very path is also present here and it is also an augmenting path. So we immediately see that if there is an augmenting path of this type, then there is one in G. Now alternatively, there is an occurrence of x on this path. So x occurs on this path. Note that all the vertices other than u are matched vertices and their matching edges are on the cycle. So none of these edges that emerge from these vertices are matching. So what you notice is that the vertex x in this graph is an unmatched vertex. Unmatched vertex can occur on an augmenting path only at one of the two ends. So that indicates that if x is on this path, then it has to be like this. If the path is this, where one of the end vertices is x, then let us compute its inverse. So inverse may look like the following. Just for the sake of an example, I am drawing one. This is the cycle C, and we have a path when you compute the inverse, the last edge that is connected to x will actually go and end up in one of the vertices of the cycle. So let us assume it is one of these vertices, say this vertex in particular. So you have now this picture, what do you do with it? How do you recover an augmenting path? Now as such, this will not give you an augmenting path in the original matching. So original matching M does not provide an augmenting path out of this structure. Well, actually it does, my mistake. You can directly take this up to this. Okay, so there is an augmenting path right here. If you take I should start from an unmatched vertex here. So starting from an unmatched vertex, this path goes up to some vertex here, and then there is one of the two vertices will be a matching edge. So you follow the alternating. If this is this is actually an unmatched edge, this is the unmatched edge, that followed by the matching and unmatching, and you continue until you find an U. So if this is V, we have found an alternating path with from U to V to U, and these vertices unmatched, so it is an augmenting path. So we really don't have to do anything else. It does compute an augmenting path directly from this. So let me quickly summarize. What we have found is, one, that if we have computed H and it has an augmenting odd cycle C, then either phi inverse C is an augmenting path in G, or phi inverse C is an augmenting odd cycle in G. Then, and call this C1, then the problem reduces to the following. Then compute an alternating or path, or an augmenting path rather, compute an augmenting path in G modulo C1 and construct an augmenting path for G from it. This is the plan. So the question now is how to compute an augmenting odd cycle in H. Now let us go back and recall that every alternating odd cycle in the graph H must pass through a B edge. So let us take a look at such a B edge. And what you do is you take its two end vertices and start walking along the tree edges upwards from both. In this case, what happens is there are these two edges, they converge immediately into S. So you find an odd cycle which is an alternating odd cycle. In this case, again we walk along the tree edges. Well, fortunately again they meet at S, and again we have found an alternating odd cycle. But in general they might meet at a vertex at lower level in the tree. So let us take a look at what happens when we start from a B edge and start rising, and ultimately we meet at a vertex, call it T. And from there is a unique tree path which takes you to S. Let us focus on this structure. This is called a bloom, upside down. This is the stem and this is the flower. So we can compute this in order n time, because we already have computed the alternating path tree from H. So just tracing the tree edges, we will determine the bloom. Our goal is to compute an alternating odd cycle or alternating or augmenting path in the graph G, and for that it would be fine if we succeed in computing an alternating odd cycle in H. So there are three possibilities. First one, that T is equal to S, like we saw in our examples. Both those examples had a situation where T was same as S. Now let us take a look at, so I will use the symbol C to indicate the cycle in this. So what if phi inverse C, if you look at the phi inverse C, and remember this is S, hence this is the unmatched vertex, the only unmatched vertex in H. So this is clearly an alternating odd cycle. If this is a path not a cycle, which means the pre-images of, here is the situation, this is S and we have C here, the two edges are incident on two distinct vertices of set U in G, then this is a path, then this is an alternating path or augmenting path. So we directly find what we wanted in G. But second situation is that T is not T is equal to S, but phi inverse C is a cycle, which means even when we map them back into G, these two edges are incident on the same vertex. So this is a alternating odd cycle. We know how to proceed from this point. We already have seen that if this is an alternating odd cycle, call it C1, then all we have to do is reduce the problem to computing an augmenting path in graph G mod C1. The third option then is that T is not equal to S. In this case, when we take the phi inverse of the Bloom, what we find in G is some vertex u maybe, let us just take as an example, this is the situation where this is the vertex T, which is one of the matched vertices. S is replaced by some unmatched vertex in G. The stem has even length. This is an odd cycle where from this point to this point is an alternating path, and these two are unmatched edges. Now, in this case, when we found this structure in G, we will do the following. We will modify our original matching M into another matching M prime in the following fashion. We will remove this and make this a matching edge. So, we will take the alternating edges which were unmatched and make them matching edges, and the matching edges on the path have been rendered unmatching edges. So, we find an alternative matching. This is still a matching where all the other edges are as it is. Note that this is an even length path, so the number of edges which have been made matching is equal to the number of edges which were non-matching, we have been turned into non-matching. So, the size of M is equal to the size of M prime. What is interesting about this is that this U has been now turned into a matched vertex, and T has been turned into an unmatched vertex. In this matching M prime, this is now an alternating odd cycle in M prime. So, what we have found is, in the first option we directly get an augmenting path, but in second and third option we have an alternating odd cycle in G with respect to some matching, maybe the original matching M or a new matching which has the same size. Now, with this, call this C1, we have the following problem. Now, the problem is to compute an augmenting path in G modulo C1. So, we have reduced the original problem of computing an augmenting path in G into this problem. An odd cycle has at least 3 edges. So, 3 vertices. When we shrink them into a single vertex, at least 2 vertices are fewer in this graph than in the original graph G. So, this is a smaller graph with at most n minus 2 vertices in it. Hence, we have reduced the original problem into a smaller problem. Either we have already solved it or we reduced it into this problem. So, this step this recursive procedure will go on for at most n recursive calls, n by 2 recursive calls. So, let us take a look at the total cost. Computing the alternating path tree from H takes order n plus m time. So, n prime and m prime may be less than or equal to original n and m. So, let us not worry about it, we will just take the worst case. We take order n plus m time to compute the tree. From the tree, we construct the bloom in order n time, and from the bloom we go back, compute the inverse image, and if necessary modify the matchings and compute an alternating odd cycle with respect to original or a modified matching. So, all this costs us additionally order n time, because the number of edges involved here are order n. So, this entire first step is order n plus n. By this we have already computed the augmenting path, or we are going to now recall this procedure, and this will go on for order n time, and after the maximum number of such recalls of the procedure, we have taken this much time at most to go down to the lowest level, where we have either discovered an augmenting path or we have concluded that there is no augmenting path. So, one step in the whole procedure of computing an augmenting path takes this much time, and earlier we had already shown that the total cost is order n times f, which is order n times n times n plus n, which is order n square n plus m.